Welcome to this walkthrough of LeetCode problem number 788, rotated digits. In this problem, we'll explore the fascinating concept of determining how many numbers between 1 and n are considered good after rotation. By the end of this session, you'll have a clear understanding of the problem requirements and the strategies to solve it efficiently. Let's dive in. In this problem, we need to determine how many numbers between 1 and a given integer n are considered good numbers. A number is classified as good if, after rotating each of its digits individually by 180 degrees, it remains a valid number and transforms into a different number. The rules for rotation are as follows: the digits 0, 1, and 8 remain unchanged when rotated. Digits like 2 and 5, or 6 and 9, transform into one another. However, digits 3, 4, and 7 are invalid, meaning they cannot appear in any valid rotated number. Given this, our task is to count all such good numbers between 1 and n, where n falls between 1 and 10,000. The output will be this count. For instance, consider the case where n equals 10. Here, the good numbers are 2, 5, 6, and 9. Let's go through them. 2 rotates to 5, 5 rotates to 2, 6 rotates to 9, and 9 rotates to 6. Each of these is valid and transforms into a different number. However, numbers like 1, 8, and 0, while valid after rotation, remain the same and are therefore not good numbers. This gives us a total of 4 good numbers in the range from 1 to 10. Now let's look at another example, where n equals 20. In this case, we find 9 good numbers. Beyond the single-digit good numbers 2, 5, 6, and 9, we also have multi-digit numbers like 12, 15, 16, 18, and 19. For instance, 12 rotates to 15, 15 rotates to 12, 16 rotates to 19, and 19 rotates to 16. Notice that all these numbers transform into valid and different numbers upon rotation. While 18 is valid, it remains unchanged, so it is not included as a good number. Finally, consider the edge case where n equals 1. Here, there are no good numbers. The only number, 1, is valid after rotation but remains unchanged, so it does not meet the criteria of being a good number. Additionally, we should consider cases where n contains invalid digits like 3, 4, or 7. Such digits make it impossible for a number to be valid after rotation. When n is large, it becomes important to check all numbers efficiently to identify the good ones. These constraints and edge cases help us ensure our solution is robust and handles all possible inputs up to the given limit. To solve LeetCode problem number 788, we need to determine how many numbers between 1 and n are considered good after rotation. A good number must meet 2 conditions. First, all its digits must remain valid after rotation, and second, the number must transform into a different number. The brute force approach is the most straightforward way to tackle this. Here, we iterate through every number from 1 to n, rotating each digit based on a predefined mapping. For instance, digits like 0 and 1 remain the same, while 6 becomes 9 and vice versa. After rotation, we check if the number is still valid and ensure it differs from the original. While this method is easy to understand and implement, its major drawback lies in efficiency. A large n means processing and validating many numbers, leading to a time complexity proportional to both the range of numbers and their digit count. Additionally, the space complexity is modest, limited to temporary storage for digit manipulation. However, for larger inputs, this approach becomes computationally expensive and impractical. A more efficient alternative to brute force is the digit dynamic programming, or digit DP, approach. This method capitalizes on the fact that the problem revolves around constraints tied to individual digits, making it a perfect candidate for digit-based dynamic programming. The idea is to treat the number as a sequence of digits and evaluate it step by step. Using DP states, we can track critical information, such as whether the number remains valid, whether it has already transformed into a good number, and how it compares to the upper limit n. By systematically exploring all possible digit combinations that satisfy these constraints, and caching results with memoization, we avoid redundant calculations. This approach is not only efficient but also elegant, as it systematically addresses all key conditions of the problem. The complexity is driven by the number of digits and the possible states, making it significantly faster than brute force for large inputs. Alternatively, some might consider pre-computing all possible rotations up to n and storing the results. This avoids recursion but comes at the cost of high memory usage, as we must maintain a lookup table for every number. While simpler, this trade-off in space efficiency makes it less appealing for very large n. The digit DP approach emerges as the most robust and scalable solution for this problem. It overcomes the inefficiencies of the brute force method and avoids the memory overhead associated with pre-computing rotations. Its systematic use of DP states allows for clear handling of constraints like valid digits, transformation detection, and bounds comparison. Additionally, memoization ensures that no computation is repeated, optimizing performance for large inputs. The main reasons to choose digit DP are its efficiency and scalability. It handles very large inputs, such as n up to a billion, with ease, thanks to its logarithmic scaling with respect to n. While it is slightly more complex to implement compared to brute force, the trade-off is well worth it for the performance gains. The modular design of its states also makes debugging and extending the solution more manageable. Overall, digit DP strikes the best balance between speed, memory usage, and maintainability, making it the most suitable choice for solving the rotated digits problem. The rotated digits problem challenges us to count how many numbers between 1 and n are good after rotation. A number is considered good if it meets two criteria. First, every digit in the number must remain valid when rotated. Valid digits include 0, 1, 8, 2, 5, 6, and 9. For example, 2 rotates to 5, and 6 rotates to 9. Digits like 3, 4, and 7 are invalid because they don't form recognizable numbers when rotated. Second, the rotated number must differ from the original. For instance, 2 becomes 5 after rotation, so it's good, but 1 remains 1, so it's not good. To evaluate this, we start by mapping valid digits to their rotated counterparts. This mapping includes digits that don't change, such as 0, 1, and 8, and digits that do, such as 2 to 5 and 6 to 9. Invalid digits like 3, 4, and 7 are disallowed entirely. This mapping is the foundation for determining both validity and whether the number changes after rotation. To determine how many numbers are good, we iterate through all numbers between 1 and n. For each number, we convert it to a string so we can check each digit individually. We use two flags. Is_valid ensures that all digits in the number are valid, while is_good tracks whether any digit causes a change when rotated. Next, we examine each digit of the current number. If the digit is not in the valid set, like 3, 4, or 7, we immediately mark the number as invalid and stop checking further. If the digit is a changing digit, such as 2, 5, 6, or 9, we set is_good to true. After processing all digits, we count the number as good only if it is valid and is_good is true. Once we finish iterating through all numbers, we return the total count of good numbers as the final result. This approach is built on a few key insights. First, validating each digit individually keeps the logic straightforward and ensures correctness. Processing digits one at a time allows us to handle both validity and rotation changes efficiently. Second, we save computation time by exiting early if we find an invalid digit. There's no need to check the remaining digits of the number if one is invalid. Third, the is_good flag ensures we only count numbers that actually change after rotation, which prevents false positives. Now, let's consider the supporting data structures. A set is used to store valid digits, enabling O(1) lookup during validation. Additionally, converting numbers to strings simplifies digit-by-digit iteration, as we can easily access each character and check it against our rules. Let's go through an example to see the algorithm in action. Suppose the input is n equals 10. We iterate through the numbers 1 to 10. For 1, its digit is 1, which is valid but doesn't change when rotated, so it's not good. For 2, its digit is 2, which is valid and changes to 5, so it's good. For 3, its digit is 3, which is invalid, so it's not good. Continuing this process, we find the numbers 2, 5, 6, and 9 are good, giving us a total count of 4. Now, regarding complexity, the time complexity is n*d, where n is the input number and d is the average number of digits per number. This is because we process each digit of every number. The space complexity is O(1), as we only use a constant amount of extra space for validation and tracking flags. This solution aims to count how many numbers between 1 and n are considered good after rotation. A number is good if all its digits remain valid when rotated and at least one digit changes to a different valid digit. The function begins by defining two sets of digits. The valid_digits set contains digits that remain valid when rotated, 0, 1, 8, 2, 5, 6, 9. The good_digits set contains digits that change to a different digit upon rotation, 2, 5, 6, 9. These sets are used to evaluate each number. A count variable is initialized to 0 to keep track of how many good numbers are found. The function iterates through all numbers from 1 to n, inclusive. For each number, it converts the number to a string so that the digits can be checked individually. The all function checks if every digit in the number is in the valid_digits set. Simultaneously, the any function ensures that at least one digit in the number is in the good_digits set. These checks ensure that the number is both valid and good. If both conditions are met, the count is increment. After completing the loop, the function returns the total count of good numbers. This solution has a time complexity of n*m, where n is the input number and m is the average number of digits in each number. The implementation is simple and leverages Python's set operations for efficiency, making it easy to understand and maintain. Here, we begin the Java implementation by defining a class called solution with a method named rotatedDigits that takes an integer n as input. The goal is to count how many numbers from 1 to n are valid rotated numbers. To achieve this, we first define two strings, valid digits, which contains all digits that remain valid after rotation, and good digits, which contains only those digits that change into a different valid digit, making the number good. We initialize a variable count to 0, which will keep track of the valid rotated numbers. Next, we use a for loop to iterate through all numbers from 1 to n. For each number, we convert it to a string so we can process its individual digits. Then, we set two flags, is valid to true, assuming the number is valid unless proven otherwise, and has good digit to false, which will update if we find at least one good digit. Inside the loop, we use a nested loop to check each digit of the number. If a digit is not in valid digits, the number is invalid, so we set is valid to false and break out of the loop. If the digit is in good digits, we set has good digit to true, indicating the number might be good. Finally, after checking all the digits of the current number, we evaluate the two flags. If the number is valid, meaning is valid is true, and it contains at least one good digit, indicated by has good digit being true, we increment the count. After processing all the numbers from 1 to n, we return the count, which gives the total number of valid rotated numbers. This straightforward approach ensures we efficiently check each number and its digits while adhering to the problem's constraints. To solve this problem, we start by initializing a few key variables. First, we define valid_digits, which contains all the digits that remain valid after rotation, 0, 1, 8, 2, 5, 6, and 9. Next, we define good_digits, a subset of valid_digits that contains digits that change to another valid digit after rotation, 2, 5, 6, and 9. Finally, we initialize a counter, count, to 0, which will track the number of good numbers we find. With these initializations in place, we begin iterating through the numbers from 1 to 10. For our first iteration, where number equals 1, we convert number to a string, resulting in number_str equals 1. We then check if all digits in number_str are valid. Since 1 is in valid_digits, this check evaluates to true. Next, we check if at least one digit in number_str is good. Since 1 is not in good_digits, this check evaluates to false. Therefore, number is not a good number, and the count remains 0. Now we move to the next iteration with number equal to 2. After converting number to a string, we have number_str equals 2. Checking if all digits in number_str are valid, we see that 2 is in valid_digits, so this condition is true. Then, we check if at least one digit in number_str is good. Since 2 is in good_digits, this condition is also true. As a result, number is a good number, and we increment the count by 1. Later, at the final iteration with number equal to 10, we perform the same checks. Converting number to a string gives number_str equals 10. Checking if all digits are valid, both 1 and 0 are invalid underscore digits, so this condition is true. However, when checking if at least one digit is good, neither 1 nor 0 is in good underscore digits, so this condition is false. Therefore, number is not a good number, and the count remains at 4. The final output for this example is 4. In this example, we now evaluate numbers from 1 to 15. The initialization remains the same as before, and we start iterating through each number. Let's highlight two specific cases here. First, with number equal to 12, we convert it to a string and get number underscore str equals 12. Checking if all digits are valid, both 1 and 2 are invalid underscore digits, so this condition is true. Then, checking if at least one digit is good, we see that 2 is in good underscore digits, which makes this condition true as well. Therefore, number is a good number, and we increment the count. Now, for number equal to 15, converting it to a string gives number underscore str equals 15. As before, all digits are valid because both 1 and 5 are invalid underscore digits. Additionally, at least one digit is good since 5 is in good underscore digits. Thus, number is a good number, and we increment the count again. The final output for this example is 6. In this final example, the range of numbers we evaluate is from 1 to 1. We initialize the same variables as before and proceed with the single iteration for number equal to 1. Converting number to a string gives number underscore str equals 1. Checking if all digits are valid, we confirm that 1 is invalid underscore digits, so this condition is true. However, when checking if at least one digit is good, we find that 1 is not in good underscore digits, so this condition is false. As a result, number is not a good number, and the count remains 0. The final output for this example is 0. The time complexity of the solution can be broken down into several steps. First, we have a loop that iterates over all integers from 1 to n. This contributes n to the time complexity, as we are explicitly processing every number in the range. Next, for each number, we convert it to a string using the str function. The cost of converting a number with k digits to a string is proportional to k, or the number of digits. For numbers in the range from 1 to n, the maximum number of digits is log 10, n. Therefore, summing up the cost of string conversion for all numbers from 1 to n results in a total complexity of approximately n asterisk log 10, n, which accounts for the cumulative number of digits across the range. Finally, we validate each digit of the string representation using the all and any functions. These checks involve iterating over the digits of the number, and since each lookup in the predefined sets happens in O(1) time, the validation cost for a number with k digits is k. Summing this across all numbers again results in n asterisk log 10, n. When we combine these components, the overall time complexity of the solution is n asterisk log 10, n. Now, let's analyze the space complexity. First, we consider the storage used for constants. The sets valid underscore digits and good underscore digits are predefined with a fixed number of elements, so they occupy O(1) space. Next, we account for the temporary storage used during string conversion. Each number is converted to a string representation, which temporarily requires k space for a number with k digits. The maximum value of k, for numbers between 1 and n, is log 10, n. However, since this storage is reused for each number as the loop progresses, the temporary space usage is limited to log 10, n. Finally, we have a counter variable that tracks the count of valid rotated digits. This is a single integer and requires O(1) space. Adding these together, the overall space complexity of the solution is log 10, n. Looking at the problem from a comparative perspective, we could also solve it using a brute force approach. In that case, we would rotate each number and explicitly construct the rotated version to check its validity. However, this would involve additional operations such as reconstructing the number after rotation, which would add significant overhead. By contrast, the current solution is much more efficient. Instead of directly constructing rotated numbers, it uses the predefined sets to perform constant time lookups for digit validity and goodness. This optimization ensures that the time complexity remains n asterisk log 10, n, avoiding the extra overhead of constructing rotated integers. Now, considering best, average, and worst-case scenarios, the time complexity remains consistent. In the best case, even if all numbers are valid rotated digits, the algorithm still processes all numbers, so the complexity is O, n asterisk log 10, n. Similarly, in the average case, some numbers might fail validity checks early, but since all numbers are still processed, the complexity doesn't change. Finally, in the worst case, where every digit of every number is evaluated, the complexity remains O, n asterisk log 10, n. To mathematically validate the big O analysis, let's break it down. For a range of n numbers, each number has up to O log 10, n digits, and each digit is checked against the predefined sets in O, 1 time. Multiplying the number of iterations, O, n, by the cost per number, O log 10, n, gives a total time complexity of O, n asterisk log 10, n. On the space side, the dominant factor is the temporary string storage. The size of the string is proportional to the number of digits in the largest number, which is log 10, n. Therefore, the space complexity is O log 10, n. This analysis confirms that the solution is efficient both in terms of time and space, making it well suited for handling large inputs efficiently. In this section, let's address some common mistakes to avoid when solving the rotated digits problem. First, there's the issue of misidentifying which digits are valid after rotation. Remember, the digits 0, 1, and 8 remain unchanged, while 2 becomes 5, 5 becomes 2, 6 becomes 9, and 9 becomes 6. Digits like 3, 4, and 7, however, are invalid because they can't form valid numbers when rotated. Another mistake is assuming that all valid numbers are automatically good numbers. For a number to be a good number, at least one of its digits must change after rotation. This means numbers like 1 or 8, which stay the same, don't qualify. Lastly, overcomplicating the solution with excessive string manipulations can lead to inefficiency. Instead, you should leverage arithmetic operations, like modulus and division, to extract and manipulate digits more cleanly and efficiently. Another mistake to watch out for is inefficiently iterating through all numbers from 1 to n. While this approach might seem straightforward, it results in an O, n, time complexity, which can be too slow for large values of n. Instead, techniques like dynamic programming or memoization can optimize the solution by avoiding redundant calculations. It's also crucial to handle edge cases. For instance, if n equals 1, there are no good numbers, or if n contains invalid digits like 3, 4, or 7, those numbers should be excluded. To ensure accuracy, always test your solution with both small values of n and edge cases involving invalid digits. This will help you catch potential errors early and ensure your approach is robust. When tackling this problem in an interview setting, it's important to focus on optimizing your solution for larger values of n. While brute force might work for smaller inputs, it doesn't scale well. Demonstrating your ability to use efficient digit manipulation techniques, such as extracting digits with modulus and division, can highlight your understanding of number theory fundamentals. Additionally, clearly distinguishing between valid, good, and invalid numbers is an opportunity to showcase your attention to detail. Interviewers appreciate when candidates can articulate the trade-offs between approaches, like the simplicity of brute force versus the efficiency of dynamic programming. This ability to justify your choices can make a strong impression. If you're looking to deepen your understanding or practice related concepts, there are several LeetCode problems worth exploring. For example, problem number 247, strobogrammatic number 2, involves generating all strobogrammatic numbers of a given length, which builds on the idea of rotations. Problem number 246, strobogrammatic number, focuses on checking if a single number is strobogrammatic, which is a simpler variation of this problem. Problem number 842, split array into Fibonacci sequence, shares similarities in its use of digit manipulation and recursion. Lastly, problem number 400, nth digit, challenges you to efficiently work with digit positions in number manipulation, which can reinforce the skills needed for rotated digits. Now let's consider some alternative approaches and their trade-offs. The brute force approach involves checking every number from 1 to n to see if it meets the criteria for a good number. While this method is simple to implement, it has an O, n, time complexity, making it inefficient for large inputs. A more optimized approach is dynamic programming, where you store and reuse results for smaller subproblems, significantly reducing redundant computations. This method is more efficient, with a time complexity of digit underscore length caret 2, but it does require additional space and careful implementation. Another option is the digit-based iterative approach, which processes each digit of n directly. This method is efficient for smaller values of n and avoids unnecessary computation by terminating early if invalid digits are encountered. However, it can become tricky to handle all edge cases correctly. Each approach has its strengths and weaknesses, so it's important to choose the one that best fits the constraints of the problem. Great job making it through LeetCode problem number 788, rotated digits. To summarize, we analyzed how to identify good numbers using efficient digit-based checks. This problem is a fantastic exercise in modular arithmetic and constraint handling. Don't forget to practice similar problems to solidify these concepts. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!